Hello, students. So let's try to see what kind of an exponential generating function I get for the Bell numbers. So remember, we have a recurrence, k equals 0 to n of n choose k, bk. Okay, and suppose we want to find this. Okay, so we want to find out what b of x is. Now, I'm going to leave this n plus 1 here because that's just going to be a left shift by 1. So we'd be starting with b1, b2, b3, and so on. In order to do that with an exponential generating function, all we need to do is take a derivative. So this is going to be b prime of x. That will give us my bn plus 1 x to the n over n factorial. And then I can just plug in from here, okay, because that's equal to this. So what do I get? I get this, k equals 0 to n of, well, no, I have to, sorry, I'm plugging that on the inside. So this is the sum from n equals 0 of this, which is k equals 0 to n of n choose k b sub k x to the n over n factorial, like that. Okay, so let's think about this for a moment. Now, if you remember before, we actually had a way of recognizing when an exponential generating function is a product. As a matter of fact, let me just grab that page right here. So if we see something that looks like this inside the coefficients, for the coefficient of x to the n over n factorial, this is the product of two exponential generating functions, one with the coefficients a and ai, and one with the coefficients bi, or an and bn. So what do I have here? Well, I have this exact thing. These are my coefficients. So this is just because what we need is we need a product here. That's the only thing that separates this from looking just like this. Okay, so now I've written this as a product. Okay, so what am I going to get? Well, I'm going to get that this is going to be equal to a product of two generating functions. One is the exponential generating function with this as the coefficients. Well, that would just be b of x. The other would be the exponential generating function with 1 as its coefficients. So which exponential generating function has coefficients 1, 1, 1, 1, 1? And by that I mean as the coefficient of x to the n over n factorial. Well, that would be e to the x. So this is just going to be b of x e to the x. Okay, so from this we get the equation b prime of x equals b of x e to the x. Now this is a differential equation. It's a differential equation of the form dy dx is equal to y times e to the x, just substituting in our y for b of x. Okay, now you might not remember too much about differential equations. That's fine. We can actually separate this. We can do this here. Yes, it is legal. Consult your differential equations people for that. We're not going to go on a tangent here because we have to get to the end. We have to find this generating function. So what does this give me? It gives me log y is equal to e to the x plus a constant. Okay. So what does that tell me? Well, this tells me y is going to be e to the x plus c. Okay, so what am I going to need? Well, I know that let's go back all the way to this. What happens if I plug in 0 for x? What should I get? If I plug in 0 for x, I'm going to get b sub 0, which is 1. So I need to get 1 out when I plug in 0 for x, okay? So if I get 1 out when I plug in 0 for x, well, this is 1 is equal to e to the 0 is 1 plus c. And the only time I'm going to get e to the x is 1 is if 1 plus c is, if x is 0 or 1 plus c is 0. So I get c equals minus 1. So I'm going to have now that b of x is going to be e to the x minus 1. And that is my exponential generating function for the Bell numbers. And then maybe let's take a moment and just enter this quickly in Python. I'll pause so you don't have to watch me type. Okay, so I've just entered this into Python. E to the x minus 1. For the generating function, I'll just take the first 10 terms. And then, since this is an exponential generating function, I'm multiplying each of these coefficients by n factorial. And let's see what I get. I get 1 for the 0 term, and then I get the 1, 2, 5, 15. And then I can get as many terms of this sequence as I need using this method. So yeah, this is a really beautiful example. We got to even see some differential equations come in. Differential equations can be used very effectively together with generating functions. We don't always need it. We don't necessarily seek to use it, but there are some situations where it comes in very handy, especially with exponential generating functions when we know what differentiation, we know what differentiation does in both cases, but where differentiation is just a shift. So you have a b sub n plus 1 or something sub n plus 1, and we instead end up getting a differential equation that we need to solve at the end. So a nice example of the Bell numbers and exponential generating functions.